All right, so let's just talk a little bit more about the idea of the independence of horizontal and vertical motion. So this trace, this image, I think is kind of helpful because it helps us to think about what is going on in each direction, because we actually have some values that we can look at and compare. So what you'll notice is this is a cannonball that's launched horizontally, so it's launched straight outwards, and so it starts with only a horizontal velocity of 20 meters per second. You'll notice that we call this the initial horizontal velocity. And if you just focus on the parts of the motion that are the horizontal, right? If I just cover up all of these vertical ones and we only look at the horizontal, you'll notice that it's always 20 meters per second, okay? So the fact that this thing is also falling down doesn't change anything about the fact that horizontally the ball is moving to the side at 20 meters per second. So the initial horizontal velocity, whatever the velocity was when it was shot from the cannon, the horizontal velocity is always going to be equal to that. But vertically, you can see what happens. Well, we start with no vertical velocity. After it's been falling for 1 second, we've got this much vertical velocity. That's increasing, 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 increasing. So it's speeding up as it's falling downwards, even though it's always going the same exact speed to the side. Okay, so it's changing, it's growing, it's speeding up vertically while it's going the same exact speed horizontally. Okay. All right, now we're going to get into a little bit of the math associated with projectiles. So again, remember that horizontal direction is going to be constant velocity. And vertical is going to be accelerating because of gravity. Okay, so that's the value that we're going to use for our acceleration. So because horizontal velocity is constant, these are the only pieces of information that we might need to know about the horizontal motion of an object. We might want to know how far it's moving horizontally, how fast it's moving horizontally, and how much time it takes to do that. And that can be summarized by one single equation. Distance in the x direction equals velocity in the x direction multiplied by time. On the vertical side, since there's acceleration, there's a little bit more that we might need to know. So we might still be interested in a distance in the y direction. That would be like the height. We might want to know the velocity in the y direction, but now we could have an initial velocity in the y direction and a final velocity in the y direction because it's changing. It's not always the same. We know we have acceleration, and we know the value of that acceleration. And then we could still be interested in time. Okay, so on this side, there's really two equations, but we're going to see it in three forms that we want to know about. So the first one is velocity in the y direction, let me not mess that up, equals acceleration multiplied by time. But then we could have distance in the y direction equals 1/2 acceleration multiplied by time squared. And I can rearrange that formula to give me an equation for time. 2 times the distance in the y direction divided by a. So these are the equations that we're going to use for vertical motion. This is our equation for horizontal motion. You'll notice that time is on both of these, right? So if you find time on one side, you can put that on the other side. So usually finding time is sort of the trick to solving these problems. All right, so here's an example of one. A ball rolls off a 3-meter high shelf and it lands 4 meters away. How much time did it take to fall, and what was its initial horizontal velocity? So I'm going to take the information from my problem and I'm going to make myself a little table and I'm going to input that information into my table. So a ball rolls off a 3-meter high shelf. Well, height is like a distance in the y direction. So I'm going to put that over here on my dy, 3 meters. It lands 4 meters away. Well, that's like a distance in the x direction. So if you imagine what this is looking like, here's my shelf. Here's how far away it lands. So we know that the ball is going to go something like this. Okay. So 4 meters away, that's how far it goes in the x direction. We know that it's horizontally launched, so that tells us we don't know what this value is yet, but we do know that it's not moving, it's not launched at an angle, so it doesn't have a vertical component. So the initial vertical velocity is 0. We know that the acceleration due to gravity is 10 meters per second squared. All right, so let's see if we can use our equations here or here to help us solve some of this problem. Well, I really want to know how much time it takes to fall and the horizontal velocity. So I really want to find out these two things. But if you look over here, right, I don't have enough information to put into this equation to be able to solve for the variables. So I need to start over on this side. So looking at everything I've got distance. I know that there is no vertical velocity to begin with. I know there's acceleration, and I want to find time. So if I check out my equations here, here's one for time. Let's see if I know enough information. I know the distance in the y direction, which is 3, and I know the acceleration, which is 10. So I can actually use that formula to solve for the time. So I'm going to say the time is equal to the square root of 2 times the distance in the y direction, which is 3, divided by the acceleration, which is 10. So when I work that out, I get the square root of 6 divided by 10, or the square root of 0.6, which gives me 0.77 seconds. Okay, so that's how much time it takes to fall. So that's the question. That's the answer to the first part. Now remember that time is shared on both sides. So however much time here, that's how much time it has over on this side as well. All right, now if I check out my formulas, right, I wanted to find the velocity in the x direction. Well, now I can use this formula right here to do that because I know the distance in the x direction and I know the time. So I've got 4 equals velocity in the x direction multiplied by 0.77. I'm going to divide both sides by 0.77 so that I can isolate my variable of interest. And so velocity in the x direction is 5.19 meters per second to the side. Okay, so that's how we can figure out the time to fall, and in this case, the horizontal velocity for our object. All right, the very last thing I want to talk about is just what happens when we launch things on an angle. We aren't going to actually do any calculations here, but I just want you to sort of see what happens. And you probably could have guessed that this is what would happen. We've talked mostly about horizontally launched projectiles, but sometimes, like if you're playing golf or if you're playing basketball, if you're kicking a soccer ball, you don't just kick something or move or throw something or hit something horizontally. You're actually going to hit it up on an angle, which means that it's going to go up into the air, come back down, and it's also going to be moving to the side. Well, it turns out that 45 degrees is the angle that will give you the maximum range. Okay. It means that it's going to give you, it's sort of a balance. It's, if you think about the components that make that up, right, the horizontal and vertical components, 45 degrees is a balance. It's a balance of Vx and Vy, which means that the object is going to have kind of balancing out the amount of time that it has to fly and how fast it's going to the side. And so 45 is going to give you the maximum range. If you go above 45, you're going to go up more. Right? And if you're less than 45, you're going to go to the side, but land quickly. So that's just a summary of what happens at different angles. So you'll notice these are less than 45. Sorry, no, this is kind of hard to see. This is 15 degrees, 30 degrees, 45, 60, and 75 degrees. Okay, so 15 degrees, you don't go very high in the air and you land pretty quickly. 30 degrees, you go a little higher in the air, but you still land pretty quickly. 45, you get that kind of balance. So you both go far and you go up. And then after that, you'll notice that most of the motion is directed upwards and not as much to the side.